Okay, let's keep going. We've got to solve now. We've got some solving to do. Okay, these are all set to 0, as you can see, right? We've got 1, 2, 3, 4 of them. Now you've got to sniff out what to do with each of these. Right, let's go for A. We've got that. Now I'm just going to turn that into a difference of 2 squares. You know how to do that now. It becomes that thing, doesn't it? Of course it does. And you know therefore that Z, what did I do there? Right, root 68 is 2 root 17, yes? It is, yes, because 68 is 4 times 17. Take the 4 out of the square rooty thing to get a 2, yeah? And you get that, and therefore you've got this, and therefore you know that Z is 2 root 17i, or minus 2 root 17. Wait a minute, where's the I gone? Just a minute. That's better. Now we are going to check our 2 superstar theorems here. Did we have real coefficients? Yes, we did. Therefore, we're expecting reals or complex conjugate pairs for our solutions. And of course, we do have a complex conjugate pair. Isn't that beautiful? Magnificent. Now, let's have a look at B now. I can't see any common factors across the whole thing, and I can't see a way of grouping these 2 by 2 to our advantage. So we're just going to have to do the old trudge-o-matic and just step through it with guess and check to find a factor and inroad into it. So I'm trying minus 1 as a value of Z, and what do I get there? Oh, that's right. It's marvellous. So therefore Z plus 1 is a factor. Yes, Z plus 1 is a factor. Now this is a marvellous result. Therefore I can say that our original polynomial is equal to Z plus 1 into Z squared plus something times Z, which I'll call alpha Z plus 5. Now how do I know that? Well, of course I know it because the leading terms must multiply together to get Z cubed. Therefore this term has to be Z squared, and the trailing terms multiply together to give plus 5, and therefore this term has to be a plus 5, doesn't it? Yeah? It's pretty nice, and therefore now I'm going to do an expansion of the Z term, just for something different, because I did Z squared on the previous example. Expansion of, and let's see what we get. Now, let's have a look at this over here. We have to work this out, the Z term. Now, if I multiply this term here by the last term, I'll get 5Z. And if I multiply this second term by the middle term, I'll get alpha Z, won't I? So therefore I've got that, yeah? Now I'm going to equate the like terms on the left-hand side and the right-hand side, and therefore I get from the left-hand side this, I get from the right-hand side that, therefore 5 plus alpha equals 2, therefore alpha is going to be minus 3. Beautiful, isn't it? Therefore we're nearly there now. We've got this times this equals 0, and I've just got to sort that out into 2 linear factors, or alternatively, have a look at this. Have a look at this. Because we're solving now, we can do it slightly differently. We can say Z plus 1 equals 0, or Z squared minus 3Z plus 5 equals 0. So instead of completing the square, we could just use the quadratic solution for that if we wanted to. And of course you know that the quadratic solution is just the result of having completed the square on a general quadratic, don't you? So therefore, let's go for it. Z would be minus 1, or Z would be this, okay? If you had ax squared plus bx plus c, you'd know it would be minus b plus or minus the square root of b squared minus 4ac over 2a, which gets you that, okay? It gets you that, which gets you to there, which gets you somewhere pretty good, pretty marvellous, and you get that. Yeah? Easy, isn't it? And of course, let's check out the 2 superstars. Yes, we have got real coefficients for that thing, therefore expecting real solutions or complex conjugate pairs, which indeed we have. Yes? Oh, wow, how sweet it is. Now, where are we up to? Mr. C. Let's go over the screen and do him. Ooh, I spot a group-a-rooney. I spot a group-a-rooney. Did you spot that? Always check that first. Always check it first. I'm going to group them 2 by 2. And I'm going to get, okay, Z squared into Z minus I from this first 2, and then I'm taking out minus 7 here, and I'm getting Z minus I in the bracket. So it's really, really easy when you do it that way. Therefore, what do I get? Z squared minus 7 times Z minus I. Therefore, now I know that z must be plus or minus root 7, or z must be I. And of course, because I don't have real coefficients here, I do get 3 linear factors, because it's a cubic, or 3 linear solutions as a result of this solving this thing. But I also don't get the conjugate root theorem working. Okay, I haven't got complex conjugate pairs. In fact, I've got 2 reals and 1 complex solution. Yeah, so that's how it works. Are you getting the idea? Hopefully you are. Now this one, I've put this one in because it's very similar to one that came up a few years ago in an exam 1 in specialist maths. In fact, it's a little bit camouflaged, but it is a group. It is a groupie. You watch. Now, I've got this. Now let's just do a little bit of a magic trick on that. I'm going to do a bit of surgery on this, and I'm going to group by taking out 5 and bracketing those 2 last terms. Okay, and I get this. Now look at the amazing result. Look at that. You see? How easy is it? How easy is it? So therefore you can then simplify that further by writing it like that. Yeah? Okay, so we're nearly there now. It just became so easy when we grouped it. So you need to be having your eagle eye at the ready for grouping possibilities. Yes, so we get this or this. So therefore, we've got z squared is minus 5, or z is root 7 plus I. And when we just continue on, we get z squared is 5i squared, or z is this, as we got in the previous line. Therefore, solving that, taking the square root of both sides for this first one, we've got z will be plus or minus root 5i, or z is that. Yeah, and of course, checking our 2 superstars, this did not have real coefficients. It certainly didn't, so we are not expecting the conjugate root theorem to apply, although, of course, being a cubic, we expect 3 solutions, yeah, which we've got, and we did not have any conjugate pairs. Well, we do. We do have one set of conjugate pairs, but this one here does not have a conjugate pair buddy. Okay, so it does not follow the conjugate root theorem. Do you see? Marvellous. Alright, let's see how you use CAS for this. It's very, very simple. You just go algebra, complex solve for C solve, or if you want to be a little bit quick about it and a little bit easier than trying to find where C is on the algebra menu, you can just write the letter C at the start of the line that you're working on, and then you can just go algebra and then solve. Okay, menu 3, 1, yeah? And then you've got a complex solve in effect. And there it is. Okay, I did a solve on that last one that we just did, and it came out exactly as we experienced, yeah? Okay, magnificent. Thanks for being with me, and we'll look forward to seeing you soon.